I need to tell you about the smallest thing that ever existed in the world of information. It is not an atom. It is not an electron. It's nothing you can touch, weigh, or see under a microscope. It's a choice, a single choice between two options. Yes or no, true or false, 0 or 1. That's a bit. And if you think this is too simple to matter, I need you to pay close attention to what comes next. Before I explain what a bit actually is, I need to show you the problem that led me to it. In the 1940s, I worked at Bell Laboratories. It was a fascinating place, full of brilliant people trying to solve practical problems: telephones, telegraphs, cables, circuits. The central question that hovered over everything was this: how do we measure information? It seemed like a simple question, but no one had a working answer. People used the word information all the time, but no one could say exactly what it was. It was like talking about temperature before the thermometer was invented. Everyone felt it, but no one could measure it. And without measuring, you can't do engineering. You can't optimize. You can't say, this system is better than that one. Cannot calculate limits, can't project anything accurately. So that was the question. Not philosophical, not abstract, practice, concrete. How do you take this thing called information and turn it into something that mathematics can manipulate? I thought about this a lot. I thought about messages, about telegraphs, about how signals traveled along wires, and I realized that the answer was hidden in the simplest place possible, in the act of choosing. Think with me. I have a coin in my hand. I'm going to throw it up. Before it falls, you don't know the outcome. It could be expensive, it could be tails, two possibilities, equally likely. When the coin lands, and I tell you it's heads, what happens? You have gained information. Your uncertainty has been resolved. You didn't know, now you know. And the amount of information you gained is exactly 1 bit. 1 bit. The smallest possible unit of information. The resolution of a single binary uncertainty. Heads or tails, yes or no. On or off. It seems ridiculously simple. But this simplicity is exactly what makes the bit so powerful. Because everything, absolutely everything that can be communicated, can be decomposed into sequences of binary choices. Let me show you what I mean with an example. Suppose I'm thinking of a number from 1 to 8. You need to figure out what it is. How many yes or no questions do you need to ask? If you're smart, 3. First question. Is it greater than 4? If so, you've eliminated half. Second question. Is it greater than 6? Third question. Is it greater than 5 or is it greater than 7? Depending on the previous answers. 3 questions. 3 bits. With 3 bits, you can identify any number between 1 and 8. With 4 bits, any number between 1 and 16. With 8 bits, any number between 1 and 256, and with 256 possibilities. You can now represent all the letters of the alphabet, numbers, punctuation, and special characters. That's exactly what a byte does. 8 bits. 8 chained binary choices, just like that. But wait, it's not just about numbers and letters. Think of a photo on your cell phone. A digital image is a grid of pixels. Each pixel has a color. Each color is represented by numbers, red, green, and blue numbers. Each number is represented by bits. A high-resolution photo can have millions of pixels, each described by 24 bits of color. Millions of pixels times 24 bits. The entire photo, every detail, every shadow, every nuance of color, everything reduced to an astronomical sequence of zeros and ones. Now think about music. A sound wave is continuous. It goes up and down smoothly. But to transmit it digitally, you sample it. Take measurements at regular intervals. Each measurement is a number. Each number is a sequence of bits. Thousands of samples per second, each 16 bits or more. The music that moves you, that makes you cry, that makes you dance is a sequence of bits, zeros and ones, nothing more. And video? Video is a sequence of photos playing quickly. Every photo is pixels. Each pixel is bits. 30 photos per second, 60, sometimes more. Billions of bits per minute. Every movie you've ever watched, every video call you've ever made, every stream, all of it is an avalanche of bits rushing through cables and airwaves. That's what fascinates me. That something so simple, a choice between 0 and 1, when repeated and combined, can represent anything. Anything that can be communicated. Text, image, sound, video, scientific data, financial transactions, messages of love, declarations of war. Everything is reduced to bits. But I need to be honest about something. When I proposed the bit as the fundamental unit of information, I wasn't inventing something completely new. The idea of using binary numbers is old. Leibniz thought about this in the 17th century. George Bull created an owl-hole algebra based on true and false in the 19th century. What I did was something different. I took this idea and gave it a precise meaning within a mathematical theory of communication. I didn't just say, let's use zeros and ones. I said, there is a measurable quantity called information. It has a natural unit, and that unit is the bit, and this quantity obeys mathematical laws as rigorous as the laws of physics. That's a huge difference. It's the difference between knowing that water boils when it heats up, and having a temperature scale with precise degrees, reference points, equations that predict exactly where and how water will boil under different conditions. Before me, people knew intuitively that some messages carried more information than others. After me, they could calculate exactly how much, and the bit is the basis of this entire calculation. It's the brick, the atomic unit. Just as physics has the meter, the kilogram, and the second, information theory has the bit. And just as you can measure any distance in meters, any mass in kilograms, you can measure any amount of information in bits. It doesn't matter what it is. It doesn't matter what it means. If it is information, it can be measured in bits. Now here's where things get really interesting, and a little strange. Because the bit is not just a passive unit of measurement, like the meter. The bit has properties. Properties that define the limits of what is possible to do with information. And these limits are absolute. The first limit is about storage. Any physical system that stores information must have at least 2 distinguishable states for each bit. A light switch is a 1-bit device, on or off. A 6-sided die can store more information, about 2.58 bits, because it has more possible states. Your hard drive stores trillions of bits, each like a tiny magnetic region pointing one way or the other. But no matter the technology, the rule is the same. To store n bits, you need a system with at least 2 to the power of n distinguishable states. There is no shortcut, there is no trick. Physics limits how many bits you can cram into a space. And this limitation is real. It comes from thermodynamics, quantum mechanics, the very laws that govern the universe. The second limit is about transmission. I prove that every communication channel has a maximum capacity, measured in bits per second. This capacity depends on the channel bandwidth and the amount of noise. The formula is precise. For a channel with a certain bandwidth and a certain signal-to-noise ratio, there is an exact number of bits per second that can be transmitted reliably. Above that, mistakes are inevitable. Below that, it is possible to stream without errors as long as you use the right encoding. Think about what this means in practice. When your internet is slow, when the video freezes, when the call drops, it's not because the technology is bad. It's because the amount of bits you're trying to send exceeds the capacity of the channel at that time. Noise has increased, signal has weakened, bandwidth has decreased. The bits don't fit. And there is no engineering in the world that can fit more bits than the limit allows. You can get close to the limit. You can optimize, but never overtake. The bit defines the limit, and the limit is absolute. The third limit is about compression. Every source of information has an entropy, measured in bits. This entropy represents the actual amount of information that the source produces. If a source has an entropy of 3 bits per symbol, it means that on average, each symbol carries 3 bits of genuine information. You can compress the message up to 3 bits per symbol without losing anything, but you can't compress below that. If you try, you lose information, destroys data, corrupts the message. This is what happens when you compress a JPEG photo with very low quality. The artifacts that appear, those ugly blocks, are information that has been destroyed. bits that were thrown away. The algorithm tried to represent the image with fewer bits than it actually needed, and the result is degradation. Entropy set the minimum, and the algorithm went below it. The bits took revenge. It's fascinating how something so abstract has such concrete consequences. The bit is not a convention. It is not an arbitrary choice of engineers. It is a fundamental property of how information works. Just as the speed of light is a fundamental limit of physics, the capacity of a channel in bits per second is a fundamental limit of communication. And just as energy is measured in joules and obeys conservation laws, information is measured in bits and obeys its own laws. I mentioned before that a bit is a choice between two equally likely options. But what if the options are not equally likely? Here's where things get elegant. If I flip a biased coin, which lands heads 90% of the time, the result still has two possibilities, but the uncertainty is less. You almost know it's going to come up heads, so when I tell you the result, you gain less information. Less than a bit. How much less? The entropy formula answers with exact precision. If the coin is fair, 50% heads, 50% tails, the entropy is 1 bit. Maximum uncertainty for two options. If the coin is 90% heads, 10% tails, the entropy drops to about 0.47 bits, almost half. What if the currency is 100% expensive, always expensive without exception? Zero entropy, 0 bits, no information, because there are no surprises. You already knew the result before I spoke. This is profound. It means that information is linked to uncertainty. Where there is no uncertainty, there is no information. A completely predictable message carries no information, no matter how long it is. A 1,000-page book that repeats the same word on every page carries almost zero information. A single unexpected sentence can carry many bits. And here comes something that people often confuse. They confuse data with information. Data is the symbols, characters, bytes stored. Information is what that data actually communicates again. You can have gigabytes of data with little information if the data is highly redundant. And there can be just a few bytes carrying a lot of information if every byte is a complete surprise. The bit reveals this distinction. It allows you to calculate with mathematical precision how much actual information is contained in a message. Not how much space it takes up, not how many characters it has, but how much genuine, irreducible information it carries. This is the difference between measuring the size of a box and measuring what's inside it. Now, let me tell you something that few people know. The name bit wasn't completely my idea. The word itself, binary digit shortened to bit, was suggested by John Tukey, a colleague at Bell Labs. He coined the term in an internal memo even before my 1948 article. But what I did was take that word and give it a central place in a complete theory. Before me, bit was just a convenient nickname for a binary digit. After me, bit became the fundamental unit of an entire science. It's like the word gene. Before modern genetics, people knew which traits were inherited, but the word gene only gained real power when it was placed within a theory that explained how heredity works. The bit is the information gene, the basic unit around which the entire theory is organized. Think about how it transformed the world. Before the bit, communications engineers worked by trial and error. They improved systems incrementally without knowing how close or far they were from optimal. They didn't have a reference standard. They couldn't say this system operates at 73% of maximum theoretical capacity. After the bit, they could. They could measure the entropy of a source, calculate the capacity of a channel, design codes that approached the theoretical limit. The bit gave them a map. Before, they were navigating in the dark. Afterwards, they knew exactly where they were and where they needed to go. And it wasn't just communications engineers. The bit has infiltrated practically all of science. Biologists use bits to measure the information contained in the genome. The human genome carries about 6.4 billion base pairs, each pair encoded by 2 bits. That's about 12.8 billion bits, or approximately 1.6 gigabytes. The entire recipe for building a human being fits into less space than a high-definition movie. This is not a metaphor, it is an actual measurement in bits of genetic information. Neuroscientists use bits to measure the rate of information processed by the brain. How many bits per second do your eyes transmit to the visual cortex? Estimates vary, but the order of magnitude is millions of bits per second. How many bits of conscious information do you process? Much less, perhaps a few tens of bits per second. The difference between what your senses capture and what your consciousness processes is astonishing. And we can only quantify this difference because we have the bit as a unit of measurement. Physicists use bits to think about black holes. There is a fundamental limit, called the Bekenstein limit, to how much information can be contained in a region of space. This limit is measured in bits, and it is proportional to the surface area of the region, not the volume. This is deeply counterintuitive. It means that the maximum amount of information that can fit in a sphere does not depend on how big it is on the inside, but on how big it is on the outside. Bits again, defining fundamental limits of the universe. The most extraordinary thing about bit is that it connects domains that seem to have nothing to do with each other. Telecommunications and genetics, computing and thermodynamics, neuroscience and cosmology. The bit is the invisible thread that connects it all. Because in all these fields, the fundamental question is the same. How much information is there here? And what are the limits to processing, storing, and transmitting it? I didn't foresee all this when I wrote my article in 1948. I was thinking about telephones and telegraphs, in copper wires and radio waves. How to send messages more efficiently. I had no idea that the same unit I used to measure the capacity of a telephone cable would be used to measure the information in a black hole. But that's what happens when you find a truly fundamental abstraction. It escapes the original domain and appears everywhere. The bit escaped. He escaped from Bell Laboratories and ended up in hospitals, where bits measure information in medical exam. It ended up on stock exchanges, where bits represent transactions worth billions. It ended up on satellites orbiting Mars, where every bit transmitted back to Earth is precious because the channel capacity is tiny and the noise is immense. It ended up in your pocket, on your cell phone, where billions of bits flow every second to show you a video of a cat. And it all started with a simple question. What is the smallest amount of information possible? What is the atom of communication? The answer is a choice. A single binary choice. One bit. Some people look at this and say it's trivial. That 0 and 1 is obvious. That anyone would have thought of that. But these people confuse simplicity with triviality. The most powerful ideas in the history of science are almost always simple once someone formulates them. Newton's gravity is simple. Einstein's equation is simple. Darwin's natural selection is simple. But before someone formulated them, no one saw them. Simplicity is not the starting point. It is the arrival point. It's what remains after years of thinking, discarding unnecessary complexity, getting to the essence. The bit is the essence of information, not because I decided it would be, but because mathematics has shown that it is. The entropy of any source is naturally measured in bits. The capacity of any channel is naturally expressed in bits per second. The laws of information are naturally written in terms of bits. It was not an arbitrary choice. It was a discovery. Information has a natural unit, just as energy has a joule and distance has a meter, and that unit is the bit. When you type a message on your cell phone and press send, billions of operations happen in fractions of a second. Your text is converted into bits. Bits are compressed to eliminate redundancy. They are then coded with strategic redundancy to protect against errors. They are then modulated into electromagnetic waves. Then they travel through the air, through towers, through fiber optic cables. Then they are demodulated, decoded, decompressed, and they appear on someone else's screen, identical to what you wrote. Each of these steps is governed by information theory. Each works with bits. Each one respects the limits that the bits impose. If a single bit gets corrupted along the way, the system detects it and fixes it. If multiple bits are corrupted, the system requests retransmission. If the channel is too noisy, the system reduces the bitrate to below capacity. This all happens automatically, invisible to you. You only see the message arriving perfectly at the other end. But behind this perfection, there is an orchestra of bits being managed with mathematical precision. People take the bit for granted, just as they take electricity for granted or running water. Nobody thinks about bit when sending a photo. Nobody thanks the bit when they make a video call with someone on the other side of the planet. But without the bit, none of this would exist, not in the figurative sense. In the literal sense. Without a fundamental unit of information, without a mathematical theory built on this unit, there would be no digital communication. There would be no internet. There would be no computers as we know them. There would be no cell phones, no GPS, no streaming, no social media, no artificial intelligence. Nothing. A single bit does nothing on its own, just as a single atom does not. But when you put together billions of them, trillions, quadrillions, structured by the right mathematics, governed by the right laws, something extraordinary emerges. The entire digital world emerges, the entire information age, the entire modern technological civilization, built on the smallest possible choice, 0 or 1. And that's what fascinates me to this day. That the most complex thing humanity has ever built, this global network of instant communication that connects billions of people, is made from the simplest thing there is. A choice, repeated billions of times per second, everywhere on the planet. At all times, a single bit can change everything. Not because he's big, but because it is fundamental. And in science, being fundamental is being everything.